In this video you will learn how not to connect a light-emitting diode to a battery. I will show you what happens in an experiment to this LED. I will explain to you why this is the case using the current voltage characteristic of an LED, and you will also learn how you can protect LEDs from too much current with a very simple measure. And finally, as always, there's going to be a summary of the most important facts from this video at the end, so stay tuned in any case. My name is Andreas from The Fearless Engineer, and here we go. Now the goal of this experiment is to show you how you should not connect an LED in a circuit. What you can see here is a typical LED, a green one, and this LED is a semiconductor, which means that under certain circumstances it conducts electricity and under other circumstances it does not conduct electricity. And we have already looked at a current voltage characteristic of such a device here, and if you have seen the video you might recall that below a certain threshold voltage this LED will not conduct any electricity at all, and above this threshold voltage the amount of current running through the LED increases very, very quickly in a nonlinear fashion. It increases exponentially. And this exponential increase is even dangerous to the LED in the sense that if too much current passes through the LED, it is likely to break. And this is what we're going to look at in this first experiment. In order to see what happens when we connect too much voltage to this LED, I have brought along a 9-volt battery, which you can see here. And 9 volts in terms of the LED current voltage characteristic is far too much voltage, and this will cause the LED to suffer a very, very high current flow, and this current flow is what we're interested in, and we're going to measure it using this multimeter here. This is connected in series to the LED and to the battery, and once we connect once we close the circuit, we will see the amount of current running through the LED here in the display. So before we start the experiment, let's quickly follow the path of the electrons through the circuit. So once the circuit is closed, the electrons leave the battery through the negative terminal, flow through the black cable, then they enter the current meter here through one of the connectors. They generate the current measurement, leave the current meter through the other connector, and then they enter one leg of the LED, generating a certain amount of light. Then they leave through the other side, where they enter the red crocodile clip here, and once this point in the circuit is passed, they enter back into the battery as soon as I connect the red crocodile clip, which you can see here, to the red wire leading directly to the positive terminal of the battery. In terms of connecting an LED, it is important to look at polarity, because an LED is only conductive in one direction, and usually the anode of the LED, which is the positive terminal, this has to be connected to the positive terminal of the battery, and usually this means the longer leg has to be connected. If you can't make out any difference between the lengths of the two legs, sometimes there's a small bend in the connector leading into the battery, or the housing is marked in a certain way that it is flattened on the anode side. Okay, so now let's start this first experiment and look closely at what happens to the LED as soon as I connect the circuit here, as I close the circuit here. As you can see, there was a spark. Also, it's smelling badly now because the LED has burned through. It's turning black now. And if you have observed what happened in the current meter, we saw a huge spike, a huge increase in current flow. Let's disconnect now. And this means that the LED has been directly connected to a 9-volt battery and has been suffering a large amount of current, far too much for the LED to bear. So this does not look like an appropriate way to connect an LED to a power source, at least not to a 9-volt power source. So let's find a better way which keeps the LED alive, hopefully. Now the reason why the LED, the green one, burned through in the last experiment, of course, was the nonlinear characteristic and this property of an LED to become highly conductive once a certain threshold is surpassed. What we have now is a new LED, a red one for now, and in series to the LED we have a resistor, and we will cover resistor in depth in later videos, and also color codes of resistor. But for now, let me tell you that this color code here indicates that the resistance value of this resistor here is at 220 ohms, which means that this linear component, this linear device here, is going to limit the current flow through the LED, and you can simply apply Ohm's law to find out to what extent the current flow will be limited. And for simplicity, for example, you might calculate this without taking into account the internal resistance of the LED. Simply connect a 220 ohm resistor to a 9-volt battery, and you will find out the maximum amount of current which will be generated by the battery for this setup. And as of course the LED itself also has a certain internal resistance, the final amount of current running through the LED and resistor in series will be even smaller than for only the resistor. And with this idea of connecting a resistor in series to an LED, we can control the current flow by choosing an appropriate value, which is set to, for example, a certain brightness value of the LED we want to achieve, or let's say a certain lifetime which we want to achieve, because smaller current flow over time also is beneficial towards the lifetime of an LED. Now let's connect the clip here to the terminal of the battery so that the circuit is closed, and as you can see here, the LED lights up, and if you observe the current meter here on the left side, this is now showing 28 milliamps, which is a perfectly healthy amount of current running through the LED. So this experiment has shown that by putting a resistor in series to an LED, we can limit the current flow, we can control the current flow, and we can also adjust the current flow to the needs of the circuit we are in. And in the videos to come, we will look at ways to arrive at a controlled value of this resistor here so that we can adapt the current flow through the LED according to the needs of the circuit we are planning on building. And to do this, I will show you how to construct a circuit on a breadboard. We will look at ways to measure current and voltage. We will look at applications of Ohm's law to arrive at the values we are looking for. So this is the first video in a series of hands-on tutorials on how to connect an LED to a resistor. Now let's quickly summarize the most important takeaways from this video here. In this video you have learned what happens to an LED that is directly connected to a battery. It literally catches fire because above a certain voltage threshold the LED behaves like a short circuit basically. Its resistance goes down and thus the current flow increases. And you can also explain this effect now using the non-linear current voltage characteristic of a light-emitting diode. And you can also use Ohm's law to calculate how large a resistor, a protective resistor, must be in order to limit the current through the light-emitting diode to a fixed value. That's all for now. If you have any questions regarding the facts in this video, please don't hesitate to drop me a comment down below. Also, if you have suggestions for future videos, leave a comment here. And this is all from me for now. See you next time here on The Fearless Engineer.